Hello, my name is David Binder, and today I will be presenting a literature survey on synchronization algorithms and methods. So let's get started. Here is the agenda for today. It's going to start with a quick synchronization primer, specifically within the areas that are germane to the subject matter in this presentation. And then we're going to explore a plethora of research papers that all have to do with synchronization algorithms and methods. And then we'll wrap up at the end with some conclusions and go from there. So let's start with the synchronization primer. Okay, so in general, synchronization refers to ensuring that operations within a circuit occur in the correct temporal order. That's the whole theory behind synchronization. Now, these systems come in a variety of flavors. They can be a fully synchronous system where that system is completely driven by a clock. You can have an asynchronous system where there's no clock, and interactions with other systems are facilitated by handshaking protocols and what have you. And then, as we'll see in a couple of these papers, there are a couple systems that exhibit globally asynchronous, locally synchronous, or GALES. So we'll see that in a couple of these papers. As I mentioned before, asynchronous pieces of a circuit, they talk to one another by use of a handshaking protocol. And these handshaking protocols are implemented in hardware in what's known as a synchronization circuit. And then finally, when you have two signals, and we'll actually see a visualization of this a little later on, when you have two signals that have the same frequency, so the same, clock period, same frequency, but they are at a phase with each other, so they don't have the exact same phase. Those are called mesosynchronous signals. We will see those in a couple of these papers as well. Okay, so let's get started with the first research paper. This is a synchronizer for a mesosynchronous system. So the goal of what these researchers were trying to do was to improve the clock frequency by having synchronous blocks and asynchronous blocks, basically. So we're back to the concept of a GALES system. These systems don't necessarily have the same phase. They have the same frequency, not the same phase. So they're mesosynchronous. And these authors are going to show us a synchronizer that is able to handle both metastability and latency characteristics. Okay. So this is what I was alluding to earlier, and this is really what I want to focus on with respect to mesosynchronous signals. So if you have two different blocks that are going to communicate with one another asynchronously, that is illustrated here through a remote signal and one of these delay signals. The delay signals will make more sense in a couple slides, but you can see they're not quite aligned with each other. So that's mesosynchronous, as I've said a couple of times at this point. And what we're trying to do in this paper, what we want to do is we want to take our local signal, which is one of these green ones, and we want to find one that aligns the best, maybe not perfectly, but the best with this remote signal. So that's what we're trying to do. And you'll see of the two examples that we have on this slide, one of them, specifically the bottom one, that seems to have the best phase alignment as compared to the other one. So it's quite nifty what these people did, actually. So we will see in the next slide. So we're sort of like zooming out as we go. So this is one part of the architecture that this team is proposing. You have a couple flip-flops that will intake The remote clock is an input. So the remote clock is being sampled X number of times. I believe in the paper, they were specifically going to sample the remote clock 5 times. And then if you look at the bottom of the screen, there's something called a transient generator. And basically what the transient generator is doing is it's taking as an input the local clock, the receiving block, the asynchronous receiving block. It's taking that local clock signal and it's going to delay it in equal delays. So you have delay clock 1, delay clock 2, delay clock 3, what have you, and they're all delayed by different amounts. And you're going to latch that D flip-flop, and you're going to get these samples at the output. And what that's going to do is it's going to enable us to see which one of these samples most closely aligns with the remote clock, sort of like in that diagram I just showed on the previous slide. So if we move on to the next slide, we'll say, here's the architecture. Here's the whole thing. So the diagram I showed on the previous slide, that is encompassing of the delayed clock up top there and the bank of D flip-flops right below it. And you see, just like on the previous slide, you have a remote clock. It comes in, and that's exactly what we saw on the previous slide. Then at the bottom there, you see something called a decision maker. The decision maker will select the closest delayed local signal out of all the choices that come out of the bank of D flip-flops, and the decoder right next to it and the multiplexer up top, those together will select that signal, the new local clock that you see on the right there. That will select the best choice. Some points of interest, all the samples that we saw on the previous slide with all of the flip-flops, all of the samples are going to occur within a single clock cycle. And we saw in the beginning, you can even see in the title, metastability tolerant, mesosynchronous synchronization. So metastability, how does that fit into here? Well, the metastability comes in by ensuring that no more than one of the samples that we saw on the previous slide and here in the bank of D flip-flops, no more than one sample will fall within the temporal range of when that D flip-flop is metastable. And restricting it to only one sample that could be metastable is enough for the decision maker to sort of say, okay, we're not going to pay attention to that sample. And so that is how this approach to a synchronizer in this type of a system works. So now we can move on to yet another synchronizer for a mesosynchronous system. And this one, I have to say, is pretty ingenious in and of itself as well. So same as last time, we have a globally asynchronous, locally synchronous, or GALS system. And the authors are going to give us a synchronizer design that also has an LCC, or local clock control. And that is the block, that local clock control is the block that's going to resolve the disagreement in phase between these two asynchronous blocks. Okay, so we're going to sort of examine this piece by piece here. So at the top, we have the clock block, and that's going to control the synchronous sender block we see on the left, and that's going to control the local clock control, the LCC, on the right, and that's going to provide a synchronous clock signal to both of those blocks. But you'll notice it does not provide a clock signal to the synchronous receiver. So where are things asynchronous? Well, things are asynchronous between the synchronous sender and the synchronous receiver. Now, that local clock control will produce a clock signal for the receiver, for the synchronous receiver, if the request line out of the FIFO that you see at the bottom, if that is high, and if there is a rising clock edge that's coming from the clock block. Now there's the magic of it. Now that local clock control is going to wait. It's not going to release a clock signal until things line up with the same clock that's on the synchronous side. And then finally, just to round this out with the FIFO, the FIFO will receive data from the synchronous sender, and that data will move through the FIFO as it goes. And once it reaches the front there, it'll send that that request signal high, and like we just described, that's one half the equation to make the local clock control pump the clock out for the synchronous receiver. And it's worth noting that this sort of a synchronization step only has to happen once while there is data within that FIFO. If there's data in the FIFO, things are synchronized. That FIFO can keep first in, first out, keep shifting the data all the way into the synchronous receiver. And there's no more synchronization that needs to be done. If that FIFO goes dry, then you would have to go through this whole process again. But that local clock control, that's key to aligning those phases. Okay. Next, this almost sounds like a heavy metal song, but I named it Counting Failures, and I think you'll see why shortly. So the authors in this paper realized that it's possible that some digital circuits just may not come out of metastability. And the way this is measured is in a metric called mean time between failures, or MTBF. And what these authors picked up on was that MTBF is getting smaller and smaller and smaller as device sizes start to shrink. So they don't have a solution necessarily for, well, how do we fix that? But they do present a solution for how can we gain more data? How can we better understand what's going on here? And that's what the contribution of this paper is going to be. Okay, so here is just a high-level overview of the measurement theory that I'm going to present here as to how they did this. So on the far left, you have your evaluation flip-flop. That's what these authors were evaluating in this paper, different sorts of flip-flops. I think there was a feedback XOR, there was another sort of feedback flip-flop. Excuse me. So that is, that's what's being evaluated, and you can see that the output of that flip-flop is being fed into two more flip-flops. Now, you will notice, though, each of the two flip-flops in the middle of the page there are not being fed by the same clock. One, specifically the top one, that top clock is going to be fed by a delayed circuit. And we're going to see why on the next slide. But that top one is going to be delayed. The one on the bottom is actually going to trigger on the falling edge of the normal non-delayed clock. So you have this span of time now between a delay and the falling edge of the natural regular clock. And the output of these flip-flops is going to be fed into an XOR gate. Well, why an XOR gate? Well, the XOR gate is going to be used because it will output 1. The XOR gate will go high if the metastability did not resolve within this time period that I just described. So basically, if both of the flip-flops are 0, if both of the flip-flops are 1, no problem. Everything's all set. But if the outputs are different, one's a 1, one's a 0, or vice versa, then that suggests metastability. The XOR gate is going to catch that, and that's going to feed that into a counter. So now we're going to have a running count of how many of these metastability events are actually occurring. So that's the theory behind their measurement. And just to back that up a little bit, here is a slide from their paper. And you can see sort of at the top there, you have the normal clock signal, and you have your delayed clock sort of right below that. And what we're focusing on here is that blue striped box region. And the beginning of that region is that first flip-flop, and the end of that region is that second flip-flop. So it's between the delay and the falling edge. And the authors are arguing if it hasn't resolved before that region, then it's in metastability, and we're going to count that per the XOR mechanism I just described. We're going to say that's metastable, and we're going to count that as a hit. And the authors do say that outside of that box, it's negligible how many metastability cases would resolve even after that point. So, so that's not included here. But this is just a visualization of how the authors went about measuring metastability events of a flip-flop. Okay. Now, Clockmaker, sort of another fun name. So just so quickly, the authors describe sort of the flow of ASIC design. It encompasses a front end, it encompasses a back end, and those areas are unique. In each, creating a clock network in either one of those regions has its own benefits and drawbacks. You can either, you can do the clock, maybe not as simply as I'm saying here, but you can make the clock in the front end, you can make the clock in the back end, and simply put, what this paper is proposing is that you create sort of a unified way of using the benefits of both of these approaches into making into a new approach into making a clock network, excuse me. So that is the contribution of this paper. The next paper, Performance in Pipelines. Again, just quickly, the authors realize there is performance degradation due to synchronization, and much as we've seen in processors in the 80s to increase throughput, the authors explore employing pipelining to overlap other computation that's required while doing the synchronization, so to sort of like hide that time cost. But they do mention that this approach of what they're doing, it requires additional hardware. So that is the trade-off that is explored in this paper. And finally, this last paper explores your environmental effects and synchronization. They note that synchronizers are adversely affected by certain voltages, certain ranges of voltages and temperature, and they propose a model that can help characterize these effects. And that is the contribution of that paper. So, so just to wrap everything up, what I've learned from this is synchronization, it's been around for a while. If you just sample the range of the papers that I've discussed here, they go from 1996 all the way up to 2015. And in this class, we're learning about it 2021. So it's been going on for decades. Also, another thing that I learned here was the concept of a Gales system is not as rare as maybe I thought it was. And in fact, some of the papers in here, that was what they focused on. Um, Another thing that seems like it was obvious from a couple of the papers is that the trend of scaling, it has an effect on synchronization. They're not independent events. So as we march down this road of continuously scaling, synchronization's going to have to continue to be looked at. And finally, I thought it was interesting that a lot of these papers merged concepts that, at least in my mind, were discrete from one another. So for example, and this is just by virtue of a Gales system, but you're creating a new system, a Gales system, from a system that's synchronous and a system that is asynchronous or self-timed. So you're merging two concepts to give you a new benefit. The same thing with the paper that was discussing the generating of clocks. You can generate your clocks in the front end, you can generate your clocks in the back end, but what if we can merge these ideas? So again, it's the concept of merging to create something even better. And just to wrap everything up, here are some references if you would like to take these for future reading. Okay, well, thank you for viewing my presentation. I hope you enjoyed viewing it as much as I enjoyed making it, and I appreciate your time.